Geometrical isomerism. What is geometrical isomerism? We know around a carbon-carbon single bond there is a free rotation, and that's why you get different conformational isomers because of the free rotation around the carbon-carbon single bond. However, if you can stop this rotation around the carbon-carbon single bond, you will get a geometrical isomerism. So therefore, for the geometrical isomerism, the necessary condition is that you should have a restricted rotation around the carbon-carbon single bond, right? So you should have a we should not have a system where you can have a free rotation around the around a particular bond. So how do we get that restricted rotation around the bond? That is pretty simple, by inserting a double or a double bond, or having a cyclic system between the two carbon atoms. Suppose if you have a carbon-carbon single bond, there is a free rotation between around this carbon-carbon single bond, but if you have a double bond, now the rotation around this bond will stop automatically. The pi bond formation, once it starts there, it will stop the free rotation around the bond, and therefore you will get a geometrical isomerism. Or you can also stop this rotation by having a cyclic ring, a cyclic system between the two carbon atoms. If you have a cyclic system here between the two carbon atoms, again that will stop a free rotation. Now we will you will get the geometrical isomerism in alkenes also, and also here in the cycloalkanes, correct? So that means for the cis-trans isomerism, or you can say the geometrical isomerism, we should have a restricted rotation around the atoms and the groups attached to each double bonded carbon, right, must be different. This is another condition, right? You should have two different groups attached to the same carbon. If you have similar groups attached to the same carbon, then you cannot have a geometrical isomerism. Let me take here an example. Suppose you got here a carbon-carbon double bond, and there cannot be any free rotation around this bond, right? Over here there cannot be any rotation. Now this is the first condition. The second condition is a particular carbon should have different groups attached. This is the methyl and this is hydrogen. This carbon, methyl and hydrogen. So each carbon has different groups. So you can have a geometrical isomerism here, and you can have a geometrical isomerism here. Now these are the two geometrical isomers. Over here we have the hydrogen atoms on the same side of a double bond. When two similar groups are present on the same side of a double bond, we call that isomer as a cis isomer. And if these groups are on the opposite side, like here, we call them as trans isomers. So this is a cis butene, and this is the trans, right? This is the trans. When they are opposite, that we call the trans butene, right? Trans butene. So these are the cis butene and trans butene. These are the geometrical isomers. Let's take one more example. If you have here a carbon-carbon double bond, and each carbon has similar groups attached to it, then because of the identical groups, you cannot have a geometrical isomerism here. This molecule will not show the geometrical isomerism. Why? Because the condition for the geometrical isomerism is that each carbon atom should have different groups attached to it. Alright, let me take another example. See here, in this molecule but1ene, this particular carbon has two different groups attached, but over here you have identical groups. So again, geometrical isomerism is not possible, right? Let's take one more example here. Here in this case, this is the cinnamaldehyde, the carbon here, two different groups attached here, and here you can see the similar groups to hydrogens. They are on the opposite side, so this will be the trans isomer, correct? This will be called as the trans isomer, trans cinnamaldehyde. And you can have another this geometrical isomerism for this molecule, where you can have the similar groups are on the same side. Let me take here, this is the C6H5 group here, and let's say the hydrogen is here, and let's say the hydrogen is here, and this is the C double bond OH. Now since the similar groups are on the same side of a double bond here, this will be called as a cis isomer, and this is its trans. So these are the two geometrical isomers. Another molecule, oleic acid. Again, you can see, each carbon atom has different groups. Here you have different groups. So this can also show the geometrical isomerism. And in this molecule, in this structure, since the two similar groups are on the same side, so this is a cis isomer. Pretty simple, right? Here again, you see in this molecule, two carbon atoms, both having different groups. Carbon has a chlorine and hydrogen, and over here these two chlorine atoms are on the same side, so this is a cis isomer. Over here these are on the opposite side, so this is the trans, right? This one is cis and this one is trans. This is pretty simple. Similar groups are on the same side of a double bond, it is cis isomer. Opposite side, it is trans isomer. Here again, can you see this molecule? The two double bonds, each carbon atom has different groups, and here you can see the two methyl groups, similar groups are on the opposite side, so this is the trans isomer, right? Now what if you have all the groups different, right? You got the chlorine and the bromine, fluorine and iodine. Should we call it cis or the trans? We don't have the similar groups to compare. Here you are comparing from the similar groups, right? If the two similar groups are on the same side, you can call it whether it is cis or the trans. But in this example, the cis and trans isomer fails, right? We cannot use this, nomenclature system for this type of a geometrical isomerism. Alright, so for these type of molecules, what we use another, this molecule can show the geometrical isomerism, that's correct, because we have a carbon-carbon double bond and each carbon has different groups attached. But we cannot use the cis and the trans terminology here, right? This molecule can show the geometrical isomerism, but we can't use the cis and the trans isomerism, the cis and trans terminology for this geometrical isomerism. For these type of isomers, we use a different terminology that is normally called as EZ notation, EZ terminology, right? So we will explain this E and Z terminology in our next lesson. Hope you got it. Thanks for watching the video. Bye for now.